Welcome to EPG Pathshala. In the present module, we are going to discuss a generalization of the Cramer inequality in case of several parameters. As in the case of the Cramer inequality, this generalized inequality also requires some regularity conditions, which involves the idea of a vector of score functions and the idea of the information matrix. The information matrix can be thought as a generalization of the Fisher's information that we have discussed in a previous module. First, we shall derive the main result, which involves the idea of non-negative definite matrices. Then we shall prove that the Cramer inequality can be obtained as a special case of this generalized inequality in case of single parameter. Finally, we shall discuss an example to illustrate the application of the generalized inequality. In this module, we consider a generalization of the Cramer inequality when there are more than one parameter. Let x equals to x1, x2 up to xn be a random sample from a population with PDF or PMF f theta, where theta is a vector valued parameter which consists of k elements, say theta 1, theta 2 up to theta k, belonging to the parameter space script theta. Consider a vector of linearly independent parametric functions g1 theta, g2 theta up to gk theta over the parameter space script theta. Let capital T, which is a vector valued statistic, consists of k elements t1, t2 up to tk, such that Ti is an unbiased estimator of gi theta for all I from 1 to k. We assume that the variance covariance matrix sigma t of T exists and is positive definite. Suppose script f theta, which is equals to f set of all f theta x such that theta belongs to script theta, be a family of joint PDFs of x which satisfies the following regularity conditions. Number 1. Script theta is an open subinterval of the real line. Number 2. The support script x, which is the set of all x for which f theta x greater than 0, does not depend on theta. Number 3. Del by del theta I log f theta x exists for all x and for all theta I from 1 to k. Number 4. For any statistic hx with expectation mod hx under theta less than infinity, the operations of integration and differentiation with respect to theta I for all I can be interchanged in expectation hx, that is, del by del theta I expectation of hx is equals to del by del theta I integral hx f theta x dx, which can be written as integral hx del by del theta I f theta x dx after interchanging the differential and the integral sign for all theta I. Number 5. The elements of the matrix capital D, whose elements are Dij, where Dij equals to del by del theta j gi theta, and for all j from 1 to k exists and is non-singular. Number 6. The elements of the information matrix capital delta whose elements are small delta ij, where small delta ij is equals to expectation over theta del by del theta I log f theta x into del by del theta j log f theta x exist and are such that delta is positive definite. Now we shall discuss the main theorem. If script f theta satisfies the above regularity conditions, then the matrix sigma t minus d into delta inverse into d prime is non-negative definite. We consider the proof of this theorem. Let S, which is equals to S1, S2 up to Sk, be the vector of score functions, where Si is defined by Si equals to del by del theta I log f theta x for all I from 1 to k. Then for each I equals to 1 to k, we have expectation of Si is equals to integral 1 by f theta x into del by del theta I f theta x into f theta x dx, which is equals to integral del by del theta I f theta x dx. Interchanging the integral and the differential sign, we get del by del theta I integral f theta x dx, which is equals to del by del theta I of 1, which is equals to 0. And for all I less than j equals to 1 to k, the covariance between Si and Sj is equals to expectation Si into Sj, which is equals to expectation over theta del by del theta I log f theta x into del by del theta j log f theta x, which is equals to small delta ij by our regularity condition. Hence, the variance covariance matrix of S is equals to capital delta. Also, for all I less than j equals to 1 to k, the covariance between Ti and Sj is equals to expectation Ti into Sj. This is because expectation of Si equals to 0 for all I, which is equals to integral Tx into 1 by f theta x into del by del theta j f theta x into f theta x dx, which is equals to del by del theta j integral Tix into f theta x dx after interchanging the differential and the integral sign, which is equals to del by del theta j expectation Tix. Since Tix is an unbiased estimator of gi theta, this is equals to del by del theta j gi theta, which is equals to small dij. Now, for any two fixed vectors u belongs to r to the power k and v belongs to r to the power k, let us define two random variables y and z such that y equals to u prime into capital S and z equals to v prime into capital T. Actually, y is a linear combination of S1, S2 up to Sk, and z is a linear combination of T1, T2 up to Tk. Then we get covariance under theta y comma j is equals to expectation over theta u prime into S into T prime into v. This is so because expectation of y is equals to 0 because expectation of S equals to 0, and we get covariance yz is equals to u prime into d into v, because the covariance between the vector s and t is equals to d. Also, variance of y under theta is equals to u prime into capital delta into u, and variance of z under theta is equals to v prime into sigma t into v. Then by Cauchy-Schwarz inequality, u prime dv whole square is less than equals to u prime delta u into v prime sigma t into v. We write this as equation 1. Now, if we set u equals to delta inverse into d prime into v, then as delta inverse prime equals delta inverse, because delta is symmetric, then from 1 we get v prime into d into delta inverse into d prime into v whole square is less than equals to v prime into d into delta inverse d prime into v into v prime into sigma t into v, which is equals to v prime into d into delta inverse into d prime into v into v prime into sigma t into v. We write this as equation 2. However, since delta is pd and d is non-singular, we have v prime into d into delta inverse into d prime into v greater than equals to 0, and from 2 we get v prime into d into delta inverse into d prime into v is less than equals to v prime into sigma t into v. This implies v prime into sigma t minus d into delta inverse into d prime into v is greater than equals to 0, and it holds for all v belongs to r to the power k. From the definition of non-negative definite matrix, we get sigma t minus d into delta inverse into d prime is non-negative definite. Now, we make the following remarks. Remark 1. For the ith component of t, variance of ti is greater than equals to summation over j from 1 to k summation over l from 1 to k dij into delta upper jl into dil, where delta upper jl denotes the jlth element of delta inverse. In particular, when k equals to 1, we have variance of t1 under theta 1 is greater than equals to d11 square into delta upper 11. Since d11 equals to del by del theta 1 g1 theta 1, we get variance of t1 is greater than equals to del by del theta 1 g1 theta 1 whole square divided by expectation over theta 1 del by del theta 1 log f theta 1 x whole square. The RHS of the above inequality is the Cramer-Rao lower bound to the variance of an unbiased estimator of g1 theta 1. Remark 2. If g equals to theta 1 theta 2 up to theta k, then we have d equals to ik, where ik denotes the identity matrix of order k. Then the theorem states that sigma t minus delta inverse is NND. Remark 3. Since sigma t minus d into delta inverse into d prime is NND and d into delta inverse into d prime is also NND. From the results of linear algebra, it follows that determinant sigma t greater than equals to determinant of d into delta inverse into d prime. After taking the determinant, we get determinant of d whole square. This is so because determinant of d equals determinant of d prime divided by determinant of delta, because we know that determinant of delta inverse is equals to 1 by determinant of delta. In particular, if g equals to theta 1, theta 2 up to theta k, then determinant of sigma t is greater than equals to 1 by determinant of delta. Remark 4 is very important. In the above theorem, we have assumed that the dimension of the parameter is the same as that of the vector of functions that we want to estimate. This need not be the case. Suppose theta be a vector with m elements, theta 1, theta 2 up to theta m, and g be a vector with k functions, g1 theta, g2 theta up to gk theta, and let capital D equals to a matrix whose elements are dij. It is a matrix of order k cross m, where dij is equals to del by del theta j gi theta for all I from 1 to k, for all j from 1 to m. Then the theorem states that sigma t minus d into delta inverse into d prime is non-negative definite for all theta belongs to script theta, which is a subset of r to the power m. This proof is exactly similar in case k equals to m. The case k less than m is usually of interest, which corresponds to, say for example, estimating theta 1, theta 2 up to theta k only, while theta k plus 1, theta k plus 2 up to theta m acts as a nuisance parameter. In this case, the theorem states that sigma t minus delta upper 1 1 is NND, where delta inverse is partitioned in the four components delta upper 1 1, delta upper 1 2, delta upper 2 1 and delta upper 2 2. Now we consider an example to illustrate the above inequality. Let x1, x2 up to xn be IID normal mu comma sigma square variables, where mu and sigma are both unknown. Let us write theta a vector which consists of two elements theta 1 and theta 2, where theta 1 equals to mu and theta 2 equals to sigma square. The PDF of xi is given by f theta x equals to 1 by theta 2 into root 2 pi into e to the power minus 1 by 2 theta 2 into x minus theta 1 whole square, where minus infinity less than x less than infinity, minus infinity less than theta 1 less than infinity and theta 2 greater than 0. Now we know that capital T1 equals to x bar and capital T2 equals to s square are unbiased estimators of theta 1 and theta 2 respectively, where x bar is equals to 1 by n into summation over I from 1 to n xi, which represents the sample mean, and s square is equals to 1 by n minus 1 summation over I from 1 to n xi minus x bar whole square, which represents the sample variance. Since x bar follows normal distribution with mean theta 1 and variance theta 2 by n, and n minus 1 into s square divided by theta 2 follows chi-square distribution with n minus 1 degrees of freedom, we get variance of T1 is equals to theta 2 by n and variance of T2 is equals to theta 2 square divided by n minus 1, where we have used the fact that variance of chi-square n minus 1 distribution is equals to 2 into n minus 1. As x bar and s square are independent, we get covariance between T1 and T2 is equals to 0. Hence, the variance covariance matrix of T is given by sigma T is a diagonal matrix whose diagonal elements are theta 2 by n and 2 theta 2 square by n minus 1. The elements of this core vector, which is equals to S1 and S2, are given by S1 equals to del by del theta 1 log f, which is equals to x minus theta 1 divided by theta 2, and S2 which is equals to del log f by del theta 2, which is equals to minus 1 by 2 theta 2 plus x minus theta 1 whole square divided by 2 theta 2 square. Then expectation del log f by del theta 1 whole square is equals to 1 by theta 2 square into expectation x minus theta 1 whole square. Since x follows normal distribution with mean theta 1 and variance theta 2, so we get expectation of x minus theta 1 whole square is equals to theta 2, and we get this is as theta 2 by theta 2 square, which is equals to 1 by theta 2. Now expectation del log f by del theta 2 whole square, which is equals to 1 by 4 theta 2 square plus 1 by 4 theta 2 to the power 4 into expectation x minus theta 1 whole to the power 4 minus 1 by 2 theta 2 cube expectation x minus theta 1 whole square. Since x follows normal distribution with mean theta 1 and variance theta 2, expectation x minus theta 1 whole to the power 4 represents the fourth order central moment of the distribution of x, and it is equals to 3 theta 2 square, and expectation x minus theta 1 whole square represents the variance of x, which is equals to theta 2. Therefore, expectation del log f by del theta 2 whole square is equals to 1 by 4 theta 2 square plus 1 by 4 theta 2 to the power 4 into 3 theta 2 square minus 1 by theta 2 cube into theta 2, which is equals to, after simplification, 1 by 2 theta 2 square, and expectation del log f by del theta 1 into del log f by del theta 2 is equals to minus 1 by 2 theta 2 square expectation x minus theta 1 plus 1 by 2 theta 2 cube expectation x minus theta 1 cube, which is equals to 0, because expectation of x minus theta 1 and expectation of x minus theta 1 whole cube are the odd ordered central moments of normal distribution. Both of them are equals to 0. As xi's are iid, we get small delta 2 2 is equals to n by 2 theta 2 square and small delta 1 2 is equals to 0. Hence, the information matrix is given by delta, it is a diagonal matrix whose diagonal elements are n by theta 2 and n by 2 theta 2 square. As in this case, D equals to I2, which is the identity matrix of order 2, we get sigma t minus delta inverse is equals to a matrix whose elements are 0 0 0 and 2 theta 2 square by n into n minus 1. It is to be noted that since T1 and T2 are respectively the UMVUs of theta 1 and theta 2, from the above example we see that the variance of T1 attains the Cramer-Rao lower bound, but the variance of T2 does not attain the Cramer-Rao lower bound. In the present module, we have discussed a generalization of the Cramer-Rao inequality in case of several parameters. We have seen that the Cramer-Rao inequality can be obtained as a special case of this generalized inequality when there is a single parameter. But this generalized inequality suffers from the same drawback as in the case of Cramer-Rao inequality, because it depends on some regularity conditions. We cannot apply this inequality if one of the regularity conditions does not hold. For example, we cannot apply the generalized inequality in case of rectangular distribution with parameters theta 1 and theta 2, because in this case the support of the distribution depends on the parameters. Again, the generalized inequality cannot be applied in case of double exponential distribution with parameters theta 1 and theta 2. This is so because in this case the derivative of log f with respect to the parameter theta 1 is undefined. Thank you.